for an external meeting.
Yeah. I was really excited to. Yes?
Is there supposed to be a single bond between nitrogen and oxygen?
Yeah, but it's also got a minus sign on it,
Oh, okay.
and so the minus sign is kind of obliterating the single bond. Yeah. It is confusing. Yeah, exactly. So this was presented in 2008 at the Southwest Regional Meeting of the American Chemical Society, and then also written up and published with the journal. Let's see, JANF. Journal. Joint Air Force, Navy, NASA, JANF. It was anyway. I could find the reference, but it's this long thing where it's research done for the Department of Defense. Okay, and I just wanted to see if they could modify the crystal habit for explosives based upon precipitation paths using the Hansen solubility parameters. So it was just sort of an open-ended question. This is related to formulation technology, so some of you may end up in pharmaceutical prep and formulation. And particle size and particle morphology have a lot to do with how you can press organic molecules into pellets, how stable those formulations are going to be, also bioavailability. So if it takes a certain amount of time to dissolve a particle in the stomach or in the small intestine, you want to match the particle size with that time constraint. So if you have a really large, bulky particle that's going to dissolve slowly versus microparticles that dissolve fast, if you want a fast-acting drug, you want the smallest particle size possible so that you have a lot of surface area and you have a fast dissolution. If you want a time release, you want a large chunk of molecule and you want it to be coated. Maybe you want to preserve its that coating until it gets into the small intestine where that drug's going to be more bioavailable. So notice how we've never changed the chemical identity of the active ingredient. We've just changed the physical properties. So tuning those physical properties could be really important. And so this is the only place I could see where a generic might not be the same as the brand name. If they're made at different factories, made with different processes, and I'm not trying to instill fear, I'm just saying that you look at them and they say they have the same active ingredient, therefore they're the same. Maybe not. If they have different particle size characteristics, they may have different dissolution properties, okay, and different bioavailability. Okay. Not that you would be able to know on a generic, but I'm just saying just because that's the same chemical active ingredient doesn't mean that it's going to have the same properties in terms of absorption. Other things too, for polymer synthesis and filled polymer formulation, these kinds of properties can be important. And I wanted to see that if we were able to see different crystal morphologies. So what's a crystal morphology? Plates, needles, gravel, what's the shape or the form, morphology, what's the form of that crystal? We'll get a certain size distribution and a certain surface area. Those are important parts. Also, crystal shape, like length to width ratios. And so these things come into play. And I think in Petrokovic, y'all do some particle counting and some particle size distributions. And so it's important in those areas. So in terms of our work, we were wanting to determine the Hansen solubility parameters of the solute, so 4-nitroaniline, and use Hansen solubility parameters to explore these different precipitation paths. I haven't seen this work anywhere else, so this idea of a precipitation path is unique to this work. And then I have seen Hansen solubility parameter dependent precipitation, but not done this way. This is a path from a dissolved substance out in different directions in the sphere and then up into water, and we'll see what we're talking about. So this precipitation path, we were taking, and this is how many of the explosives, and I think, Matthew, you even said that some of y'all's precipitation is directly into water. Is that correct? So this top path would be relevant to your precipitation, taking your substance and going straight into water. In this work, I thought, what if we changed the path and went from our good solvent, that's green, that's S, into a non-solvent, which is yellow, at a 1:9 ratio. So essentially, we've now replaced the cage, statistically replaced the cage around that solute with non-solvent molecules. And then we go from that into water, again at a 1:9 ratio. So we have a 1:10 dilution in each of these steps. So even though we're originally going straight into water, a huge dilution in water, now we're going through 2 steps, a 1:10 dilution each step. What could this give us? Well, think about a microcrystal. It's very rare that a crystal will have the same functional groups on all of its faces. So if we take a cubic crystal there, it's very common for the molecules to line up and to have 2 faces, or really 4, if you go around the crystal. If you look up there, the A faces have, let's say in nitroaniline, those are the ring faces, or the edge of the ring. And so you might have those faces be similar all the way around, but then the end faces have nitroaniline groups and nitro groups. Maybe they alternate because they're going to line up with the polar dipole moments, and they line up. You've got nitroaniline, or you've got nitro and aniline and nitro and aniline, or nitro and amine, all on face B. And at the other end of the molecule, you have nitro and amine. So the B faces are different than the A faces. You follow me? So, and this is going to be very similar in many, many crystals. I'm sure, is Dr. Norman talking to you about crystallography and the 1,1 face and the 1,1,0 and all these different faces? If you know the crystal structure for the molecule, you can sort of build one of those up in Gaussian, and you can see, yeah, these faces are all looking at the side of the molecule. These faces are looking at the end of the molecule, and they're going to have different chemical properties. So where do the chemical properties come into play? They come into play in intermolecular attractions. So solvent molecules are going to interact with the benzene ring on this molecule differently than they interact with the nitro and the amine groups. The nitro and amine groups can hydrogen bond, they're polar. So polar and hydrogen bonding molecules are going to want to associate with the nitro and amine faces differently than they associate with the aromatic ring faces. And so if they favor the B face, so think about that. You've got nitros and amines there, and you've got solvents that come in hydrogen bond. What does it take to grow that face? You've got to move the solvent out of the way. Does that make sense? In order to put molecules on that face and to grow the crystal in that direction, on the B direction, you have to displace solvent molecules. And if there's strong interactions there, then that face is not going to grow out. Okay? The A faces are going to grow, because if there's no interaction with the A face, no strong interaction, then those solvent molecules are easy to displace. And other molecules are just going to stack on those A faces, and the A faces are going to grow out, and the B face won't. Now what you'll end up with is a flat crystal over there on the right, where the B face is presented. It was stabilized by the solvent, and the A faces grew out. Do you understand what I mean by growing out? Not growing wide, but growing out. You're stacking molecules on the A face, and you're making a plate. So that's that top one, because the solvent is interacting with the B face. And so it stabilizes the B face, so you get more of it. What about the A faces? So let's come down here. If the solvent favors A and they stack around the A and sort of protect it, then it's easy to displace the solvent molecules on the B face, and then it grows out and it grows needles in this particular case. So since the A face is stabilized, you have more A surface area. And then if it favors neither, then you just have lots of nucleation and lots of growth, and you'll have gravel. You'll have particles that just grow in all directions, because there's really no problem displacing the solvent from any of the faces, A or B. Now you could probably model some of this. We just did the experiment and saw what we saw.
I guess toluene be too sterically bothered to stack nicely with anything.
It's really, I don't exactly know how to explain the toluene behavior. It just really didn't, that pi stacking just wasn't very strong. I mean, it grew in all directions. Yeah. Yeah, I just don't think that's a very strong intermolecular attraction. and I think mostly the polarity was driving a lot of these things. Yeah. And so we had to find the solubility, the Hansen solubility parameters for the 4-nitroaniline, and this was the set of notes I took to the other lecture last time, where we did the dropwise, determination of the percent by weight solubility of 4-nitroaniline in the solvents. Now, why 4-nitroaniline? The funding agency makes explosives, but we don't have the ability here at the university to handle explosives. We don't have a secure facility to receive explosives. We don't have a secure storage facility. We sort of do out at Wire Road. It's on the Gibbs Ranch, but it has, I think its explosives receiving licenses lapsed. Anyway, it's a headache. Bottom line, it's a very much of a headache to deal with explosive molecules. 4-nitroaniline is not an explosive, but it has a push-pull nature like some of the explosives. So TATB is an insensitive explosive, and it's 1,3,5-trinitro, 2,4,6-triamine. So it's got 3 amine groups and 3 nitro groups around the benzene ring. And so the 4-nitroaniline is just one piece of that, just delete 2 nitros and 2 amines. And so it has a very similar electron cloud, only it's not exactly the same, but it has the ability to form some bridging hydrogen bonds and so on. It's different in that it's polar, and TATB is not polar. But 4-nitroaniline can be handled without restrictions, and it's good for method development. So this is a good exploratory project to do with this nitroamine. And so here, using group additivity, we were able to find the Hansen solubility parameters for the explosives. And so I'll go through with the pen and kind of show you some of the ones that are there. So here's that molecule I talked about, TATB, triamino trinitrobenzene. Okay, and then DATB, so diamino trinitrobenzene, is right here. It's an impurity in TATB. And then here's 4-nitroaniline and 2-nitroaniline. These were determined using group additivity. So Van Krevelen made a group additivity model for polymers. And you can apply, you just look at how many methyl groups you have, how many aromatic groups you have, nitro groups, and so on, and those contribute to the D, P, and H values. We made a spreadsheet where you just type in 1s and 2s and 3s, depending upon all the different groups you have in your molecule, and it'll generate the Hansen solubility parameters. So sweet. There's another one by a group out of Greece. Stephanos also had a group additivity model for the Hansen solubility parameters, but they didn't have very good coverage of the nitro groups and the amine groups. And then Hoy has a solubility parameter model, but it requires the critical temperatures, and we don't know the critical temperatures for these different molecules. So we really can't use Hoy. It would be great for solvents where you know the critical temperature, pressure, and volume, but we don't always have that information. And then here's all of the different solvents that we used to test. So basically we were not too confident in this group additivity, and we wanted to do this experimentally. Here's some other explosives as well. Here's pentaerythritol tetranitrate, PETN. That's a common explosive in detonators. It's a volatile explosive, so even though a detonator may be small compared to the rest of the bomb, it's the one that stinks the most. And so if you have a sniffer, you'll smell this first. Dogs will smell this. It's an organic nitro group. And so, what's that?
Is that sugar based erythritol?
No, it's not. It's a 5-membered carbon, but the middle carbon is got 4 carbons around it. And then those 4 carbons were alcohols. And so we use those 4 alcohols to react and put organonitrates on it. So it's got carbon in the middle and then 4 CH2 groups. And on each of those CH2 groups, you have an NO3s. And so it's a totally nitrated molecule. And it's just like nitroglycerin, because glycerin, a glycerol, 3 alcohol groups, you can put 3 organic nitrates, not nitros, but nitrates on that. Very shock sensitive, the nitroglycerin is. This is less shock sensitive, but shock sensitive enough that you can use it as a detonator. Okay. And then here's hexanitrostilbene. So still being molecule, and you put 6 nitro groups on it. And then here's HMX, which was originally, I don't know, this is the story I heard. I don't know if this is true or not, but it was a British explosive, and so they called it Her Majesty's explosive. I don't know if that's true or not. But anyway, these are the results for the explosives from these different group additivity models. They don't seem completely unreasonable, but we had reason to doubt their accuracy. So we went to the HSP determination that I talked about last time, where we weigh 0.2 grams into a vial, add the solvent dropwise, record the mass, and stop when the solutes homogeneously dissolved in the solvent. And so this was the data where we went through and we scored these, and we said anything above 19% solubility in this solvent was a good solvent. Anything less than that was a bad solvent. And so we came up with the solubility sphere. So see the last lecture for the Excel spreadsheet that goes with this analysis. And so that's our 4-nitroaniline solubility sphere. And then we have it surrounded by just a few solvents that are important to this project. There were more that we used to determine the solubility parameters, but these are just some ones to show the molecules on top, like IPA. The one in the back is acetonitrile. The one on the back left is propylene carbonate. The one in the front is ethyl acetate. The bottom left is acetophenone, and toluene is way up front. And then water is straight up at 42, kilojoules per liter. So this is the scheme for this crash precipitation. We created a saturated solution of 4-nitroaniline in a solvent, and we used DMF for this study, dimethylformamine. And then we'll take a pipette and mix in 1 part, so 1 mil into 9 mils of a non-solvent while stirring. If the precipitate forms, it was pretty rare that it did form, but sometimes it did, we would filter it at that point. And so we wouldn't even need to go to water. If the solvent was bad enough that we got precipitation, then we would just precipitate it with that solvent.
You say you're solvent, you just mean a solvent that's outside of the sphere?
Yes, great. So a solvent that's outside that sphere, yes. And so we're going out of the sphere in different directions, if you think about it. Okay, so if you go to a non-solvent, you're either coming out of the front of the sphere at lower polarity, or going out of the back of the sphere at higher polarity. And so we're changing the nature around that molecule by changing out the solvent. So this is our setup, really simple stuff. And we have a light that has a little laser pointer on it. So the laser is shooting through the flask, and we're using the Tyndall effect, scattered light of particles, to tell us when we have precipitation. Although most of the time it was obvious. But if, in case it wasn't obvious, if we started to see little scintillations of crystals growing, then we would know precipitation had begun. So if you have a homogeneous solution, the laser goes right through and you don't see it. But if you start to see microcrystals, you'll see little sparks. You'll see the laser get flashed into your eye just a little bit. You'll see little red flashes from the laser. And it's a way to tell if you're starting to see precipitation. So it's a nice little, and that scattered light from particles is the Tyndall effect. So you can use the Tyndall effect to tell when precipitation is beginning. That's really helpful if you have really slow precipitation and if you want to keep it slow. So you can shine a laser through there and see if you're getting microcrystals. If they haven't settled yet, they may still scatter light. And you want to let them grow if you want to get some larger crystals. You don't want to agitate it.
As long as you're not exciting your molecule with the laser.
Well, that's true. That might be a potential, but most of the time it's just, scattering off. But yeah, you're perturbing the system a little bit, but shaking it perturbs it even more, So whenever you're growing crystals, maybe you don't know this, there's a battle going on between nucleation, so new crystals starting, and growth. So a molecule that's in solution can go to a new crystal, or it can go to an old crystal. If it goes to an old crystal, you have growth. If it goes to a new crystal, you have nucleation. And so there's these competing growth rates. And you can do different things to try to tailor one versus the other. One way to favor nucleation is to mix or create some sort of vibration in the solution, scratching the side of the flask. these little vibrational waves go through the solution, and they force these molecules together, and you can get rapid nucleation. You remember doing that in organic chemistry. You know, you recrystallize, and then you scratch the side of the flask to cause it to crash out of solution, and you'll see lots of crystals form. But if you don't scratch the flask, if you drop in a seed crystal and leave it alone, you can get large crystals to grow. Or if there's imperfections in the glass, sometimes that will start a nucleation center, and you'll get needles growing. It looks like needles are growing out of the glass. I always loved that part of organic. I hated the smells, but I loved the crystallization. And so I'd watch the needles grow, and I wouldn't touch my flask. And my friends would kind of try to knock it, you know, and I'd get really angry. So that's why they did it. So I had the 4-nitroaniline and the DMF, a bunch of little test tubes and pipettes and small beakers. It was so easy, and a stir bar. So we take the 1 ml of 4-nitroaniline, and this particular case is not to 9 ml of ethanol, and we're stirring. We see that it stays homogeneous. And so then we just take 1 ml of this and into water. So 1 ml of that into water, and you see the yellow powder. It crashed out, and we get crystals. And so then we take that yellow powder, we filter it in a filter flask, and then look at it under the microscope. So these are all of the data and lots of filter papers. I had a good set of students that semester. I kind of pitched this idea, and a couple of days later I came back, and this is what I saw on the lab bench. I mean, they just knocked through this in a couple of days, and it was amazing. That the microscope work did not go that fast. So it's really fast, easy to create a lot of precipitates, but analyzing them is where the time sink is, because we were doing this just by eye. So we were counting particles and measuring their size linked to width ratios. It was incredibly tedious. So we looked at these different non-solvents. Water, of course, all of them went into water, but we had acetone, acetonitrile, ethyl acetate, a couple of alcohols, propylene carbonate, which is a unique molecule that's very, very polar and very, very dispersive, and then toluene and hexane. And this is some of the results. So this is going straight into water. So let me sit down and walk you through some of these precipitation paths. So you see we have the solubility sphere, and the traditional method for dissolving this is to go straight out the top of the sphere to water. And so it's a 1 to 10 or 1 to 9 ratio. So our actual solution is right about there, right? 1/10 of the way back, because it's one part dimethylformamide and 9 parts water. So it's 90% of the way to water. And then we get this precipitation. And you see there's quite a few needles. Over here is 10x on the right, and we see needles. And occasionally, I have no idea, not that it's important to this, but we hit these little spheres. So I don't know, I just took a picture of it here. I've zoomed in on it. This perfect little sphere. No idea what that is. Okay.
So this is the situation where the water interacts favorably with the ends, like the nitro and the aniline groups?
Well, it potentially, haven't done a crystallographic study of this, so I don't exactly know that these are the nitro groups on the end. Okay, it was just in that slide trying to show you how you might have differences between A and B faces. Okay, so that's not been confirmed by these results. We were really just looking at the crystal habit, whether you got needles or plates or gravel. So those were our 3 categories that we saw. Now, it's very difficult, as you can see down here, whenever doing these kinds of studies, to disperse your crystals. This data right here is unintelligible because the crystals are all overlapped. And so that's me showing you that I'm not a microscopist. Okay? Because one of the techniques in microscopy is dispersing your powder under the cover slip so that you can actually get separation between your crystals and you can look at them. So you may have this whole experiment, and this is speaking in general. You may have this experiment, but if you don't have good technique in terms of your microscopy, you can't analyze it. And so that's something that I would need to work on, is my ability to disperse it. This is a little better in this middle panel. The crystals are somewhat separated, although we still have these globs. ideally, you would have crystals that were not touching each other, and then you would let the computer identify where the crystals are. Because they make software where the computer comes along and it finds a crystal. Let me do it over here. So the computer comes along and it scans and it hits an edge and it finds that edge, and then it can do an edge tracing algorithm. And it'll find those edges, and then it can darken them. It can go in and it can fill them, and then it can count up how many pixels are covered with dark pixels, and it can give you some surface area type information. It can measure the length to width ratio, and it can count. So it can give you a histogram of how many particles are in each different category of size. Yeah, that's ideal, to let a computer do your particle counting, because we were about to go blind on this microscope project, but it worked. Now, these are 15x magnification. That's as high as my microscope will go. But you can see that even just with crash precipitation, squirting 1 mil into another with a stir bar, we can start to see the crystal habits. These are not huge crystals. These are tiny little crystals. They just look like precipitates. If you were an organic, it's just a precipitate. Well, if you look under a microscope, those are crystals many times. So that's straight out of water. This is sort of the baseline. This is now going into methanol and into water. So we go out of the sphere here, 1 to 9. So we end up being 90% of the way to methanol. And then we go 1 to 9 into water. So then we're 90% of the way to water from this point. So we're right about there. So that's the environment that these crystals came from. But more importantly, I think, is this environment here where it leaves the sphere. That's when we start separating or replacing the molecules around those analytes with methanol molecules. And they're going to stabilize certain phases and not stabilize other phases. And we get, kind of similar looking crystals. We zoom in. Notice how they're much prettier. What's going on with the pretty part of the crystals? They're pink and blue and yellow. I've got crossed polarizers here. And so I'm polarizing the light that's going, hitting the molecules from below, and then I've crossed the polarizers on my eyepiece and on the camera. So the crystals have to rotate light for it to get to my detector. And the different thicknesses of the crystals rotate light different degrees. And so it's wavelength dependent. And so maybe the red light rotates enough to get through my analyzer, my eyepiece polarizer for a certain thickness. But then if it's a little thicker, maybe it rotates a little further, and then the blue light comes around and it's at the correct angle. So because this rotation is wavelength dependent and I have my cross polarizers, I have different colors based on the thickness of the crystals. Okay. And also, if you zoom in, we see some much cleaner faces compared to water. So they're not just different crystal, or not just the crystal habit's not that different, but the cleanliness of the faces are. Okay. It's probably related to the speed at which they precipitated, and so the methanol, my hand waving explanation is that the methanol associated with it a little bit more than the DMF, and then caused the crystals to grow a little bit slower. Here we're going into ethanol. Now, even though ethanol and methanol are alcohols, they are fairly different. Methanol, it came out of the sphere and went this direction. Ethanol, it's kind of coming out of the front of the sphere. It's less polar, and so we come 1 to 9 to this point, and then go 1 to 9 to water, so we get almost all the way to water. And we're starting to see some plates. Like that's what I would call a plate. These are still needles, so we're starting to see some needles and some plates. This is transmitted light, so light's going through without the polarizers, and this is with the polarizers. Okay, this is acetonitrile. So we're going out the back of the sphere to acetonitrile and then to water. So we're kind of zoomed in. Now it's a very polar molecule. We don't have any plates at all in this one. It's all needles. Then we get to acetone. We come out the front. And so it seems like when we did ethanol and when we did acetone, we came out of the front of the sphere and we got more plates. When we went out of the back of the sphere or the top of the sphere, we got needles. And so here's this a nice plate. And now what's this funny business in the middle? So it's a plate, and if you really zoom in on it, it looks a little dirty in the middle here. And this one too, it's got some mottled area too. That's solvent that was stuck to that surface and then finally came off. And so you've got pits. So you had solvent stuck to that surface for quite a while as the crystal was growing, and then finally they left behind pits. Okay? So that's really confirming that this solvent is stabilizing that face. So our idea is sort of confirmed here. We still don't know what that face is with our X-ray crystallography, but we definitely, our idea that solvent is going to stabilize the face that gets expressed is shown here with this solvent pitting. And so that's nice. And then now we get into ethyl acetate, also coming out the front. These, you might say, well, those are needles too. But these are logs. These are enormous. And there's a lot of gravel. So we've got some gravel here, a bunch of gravel here, and then look at this beam. This is enormous. It's like a 2x4 in there. And so I can't really explain that. I mean, but if you look at some of these, we also have some of these beams that are sort of stuck to each other. And then toluene. Look at this. This is, I would definitely call this gravel. So we're coming straight out of the front of the sphere to toluene and then up to water. And this one is the first one we saw, this enormous crystal here. And I zoomed in on it here. And I remember this from the experiment. This crystal grew on the glass surface. So this molecule did not like toluene at all. And it went to the glass to precipitate. And so if it was crashing out of toluene, it made gravel. But if it made it over to the glass, it associated with the glass and started growing a crystal on the glass. And so this is an important point. Sometimes the container matters. Okay? And you wouldn't know that in an industrial setting where you got a stainless steel container and it's growing on the surface of the stainless steel. You don't have a camera in there. So you don't know where precipitation is happening. So this is a really important result, even though it was one little crystal on a piece of glass on the side of the beaker. This explains certain situations because surfaces have Hansen solubility parameters too. And I've put this molecule in toluene, a solvent it does not like. And what else is in the container? A Teflon stir bar. Okay, and a glass surface. Now, this molecule is polar. It's going to like the glass. It's not going to like the Teflon. Okay, but what if I had a stainless steel tank, but I used a glass-coated impeller versus a Teflon impeller? So, you know, the glass and the Teflon impeller may produce different results, and yet you got the same temperature, same pressure, same volume, same stir rate. These are the things that engineers do to get the right crystal structure, stir rate, pressure, temperature, volume, you know. And if they're getting different results and they didn't know, well, we changed out the glass impeller with the Teflon one, they might get totally different crystal habits and not understand what changed. Because all the dials on the control panel are the same. We set the same temperature, the same pressure, the same speed on the motor, and so on. And so this happened at a company of mine that I worked for in the past, where they synthesized these molecules and got the right crystal structure at a previous facility. And they built a new facility, and they're all excited. We got updated electronics, updated controls, updated motors and everything, and it could not get the same crystal structure. They also upgraded the pot. They went from copper to stainless steel. But they had the same solvents, same speed, same everything, and they couldn't get the right crystal structures, the same crystal morphology. There's the same crystal structure from an X-ray diffraction standpoint, but not the same shape, needles and plates and so on. And so when they went back and they brought that copper pot from the former facility and installed it in the new facility, they got the right morphology. And so that I just want to take that little excursus for you to say, sometimes it's not just the chemicals that you put in there, it's the container. And you need to always remember that, because the container has a Hansen solubility profile too. It has a DP and H value, and that will change if it's not clean. And so cleaning is important as well. If you've got residue on that container, it may have a different behavior. It's very hard to clean scale off the heating element part of that container. And so if you've got scale, if you're doing things in water and you've got calcium deposits, that's going to be different Hansen solubility profile than clean stainless steel. So you might have a great reaction tank when you first install it, and then it degrades over time, or just the opposite. Maybe it needs to be seasoned a little bit. You know, this tank just doesn't do right for the first 6 months, but after a while, it really gets good. What's going on? Well, you probably have some scale building up around the heating elements, and now it's working because that scale's helping your yield.
So it's like a chemical basis to all full, like,
Yeah, there's sort of the, you know, these containers, like that container that was the old facility, had a copper surface, and that made all the difference in its crystal morphology. And then here we're going into propylene carbonate, so we're going out the back of the sphere. Very polar, but also not very hydrogen bonding. And we have another one of those spheres, those inexplicable spheres. I have no idea what that is. So here's the summary. So if you look at all the different gravels, you can look at this and say, do I see a trend at all? It's not that obvious because there's a lot of scatter in the data. Pretty much the main point is from looking at the pictures, the gravel's down here at the bottom, down, you know, towards toluene, out the front and down at the bottom. Also, propylene carbonate's pretty gravelly. Okay. So let's look at image analysis. We can take this length to width ratio. We weren't able to use computerized particle counting. We had to do all this by hand, so it was really difficult. You don't have to have a calibrated image to do length to width ratios because the units cancel since it's a ratio. But if you did have the units, you could actually calculate then surface area and so on. Look at those error bars. Pretty ugly, yeah. So we took length to width ratio on the y-axis and compared that to the polar parameter. Try to see if there was a trend in length to width ratio, because if you have a long length and a short width, you got a high length to width ratio, okay? And that's needles. So high length to width ratio is needles, low length to width ratio is gravel, okay? And up here you can see the R squared for this fitting line is 0.01. We've modeled 1% of the variation with this model, this linear model, okay? So that's great. That's no is an answer too. Now we plot it versus D value. So the highest D value is propylene carbonate, the lowest is methanol. Again, lots of error bars. So 0.28 is our R squared value, so no trend in dispersion. And we're just looking at particular Hansen solubility parameters to see if one of them is more important than the other. So here's the hydrogen bonding term. Much more spread out and a bit of a slope. Okay. Of course, just error bars. There's lots of ways to draw this line through those error bars. But for the central tendency of those distributions, we can match 69% of the variability in the data with this linear model. So there's a possible trend. I'm not going to, stake my life on it, but it's a possible trend in the hydrogen bonding parameter. Now, these are cumulative distributions, and I wanted to tell you, or use this for one of your vocabulary words when we're talking about distributions. A cumulative distribution, if you think about a Gaussian distribution, you have the mean in the middle, and you have the tails. And you have the really small particles, which are less probable, the really long particles, less probable, and then there's some average in the middle. That would be the Gaussian curve. But if you want to just integrate that from left to right, then you get the integral of that Gaussian curve, and that's what we see here. So the cumulative distribution is the integral of the frequency distribution. The frequency distribution is a histogram. So if you need me to draw it. So how many times you got a particular particle of a certain length to width ratio, you would have this average, and you'd have something like this. And so at the average, that was your most frequent measurement. Really low, less frequent, really high, less frequent. Okay, so that would be the frequency distribution. And then the cumulative distribution would be the integral of this. Okay, going up here to 1. So you've got the whole distribution here, and it's cumulative, it builds up. So that's what we're seeing up here. Now, if you had some small crystals, like a gravel form, and then you had some needles, you'd have a bimodal distribution. And if you have a bimodal distribution, then your cumulative distribution is going to go up like that, and then up like that. And so if you see two steep slopes, it's bimodal. Okay? And so we see some of that action here. The green one, coincidentally, is bimodal. See that? You see some gravel, some short length to width ratio, and then some crystals that have a little bit longer length to width ratio. And this is a very common plot for particle analysis, is this cumulative distribution. A lot of the software for particle counting equipment will give you these cumulative distributions. And so up here you see on the left is gravel, on the right is needles. And these are the different non-solvents that we use to precipitate things out. It looks like ethanol and acetone and acetonitrile were multimodal. And then we just looked at, I just wanted to see if it was more certain if we took the top 3 crystals. So what are the biggest 3 crystals in the whole, scene? And we saw a tighter distribution, like, can this solvent pair produce a big crystal? And does it have a long length to width ratio? And it's just another way. So I call these the pickers. You can get in there and pick them out and find them very easily. Now this precipitation paths are sort of some general conclusions. They all produce larger crystals than the DMF and water. So
I need clarification. When you say larger crystals, are you simply saying the area, or are you saying the length to width ratio?
The area. So whether it's a long and skinny or gravel, the area was larger for all of these than the areas I got from straight to water. So water was just all nucleation and very little growth. And so in all of these cases, we favored growth. And so in this competition between nucleation and growth, going into a non-solvent helps growth. All right. And so that whether it was needles or whether it was gravel, they were all bigger, going gently. I would say gently. You're going to a non-solvent and starting the growth process and then going to water. And in fact, in these non-solvents, if you left them there, they would probably precipitate really large crystals. And so that's what you do in the back of the hood, which I don't even like using the hood because it vibrates. But you put your reactants, your products in non-solvents in a test tube rack, covered with parafilm, which is a bit porous, and set it in a dark corner of the lab and go away. And then you get really big crystals. That's the best way to crystallize something, is put it in a slight non-solvent and let it grow slowly. And then those you can pick and go put in an X-ray crystallographic machine. Okay. What we wanted to do was more of like a flow process, where your products flow into a non-solvent and they flow into water, and that way, for industry, flow processes are way better than batch processes, where you do a batch, you work it up, and you waste a ton of time and solvent redissolving, recrystallizing, and if you did a flow process, you'd have a much better process, much more efficient process. And so our conclusions, the morphology seems to correlate with the Hansen solubility, the H parameter, the best. Increasing H should favor needle growth. Now see, the thing is, does that mean that's the better crystal habit? Maybe not. Maybe for your process you want gravel and not needles. So this tells you to avoid the hydrogen bonding solvents. If I was making a formulation and I wanted it to be fast acting, I'd go straight to water because that produces the smallest particles. If I wanted intermediate particles, I might go to propylene carbonate or to toluene, and I would get gravel, but small gravel particles. But if I wanted long needles, I might go to ethanol and go up. Okay. We only counted about less than 200 particles per system, which is pretty low. So we estimated 19,200 to go if we were going to continue this. But I think we got enough to be confident that there's a trend there. And then we showed that the solvates, meaning the solvents attached to the surfaces, those were possible and recognizable. These are the students that worked on this. Carl Kuklins has been working for GE Oil and Gas and now Suez Oil and Gas technology. John Mayer went to Baker Hughes, and he was the one I had a picture of in that Baker Hughes talk. Steve Doss, amazing PChem student, the only one that ever went through PChem just from the notes only. He didn't come to class at all. Yeah, he had family situation at the time and it was just not able to come to class. He'd show up and take the tests and nail them. So props to him for teaching himself PChem. That was even before I videoed the lectures. So, bright fellow. Katie Roethlisberger went, and now she's got her PhD. She went to A&M, and so she's doing awesome. And then Derek Blaylock went off to Pennsylvania and also worked in oil and gas in Pennsylvania. He was the guy that said he made a spreadsheet tool that just converted barrels of liquid to liters and to cubic meters and all of these unit conversions that you use all the time. He made a spreadsheet for that. And I mean, everybody in the company thought he was a genius. And they were asking him, can we have your spreadsheet? Because it's so easy to use. And so that's one of the things that I want you guys, that's that portfolio that we're going to do and aim for at the end of the semester, is to have these spreadsheet tools. And we're going to get into them in the next couple of lectures as to how to use the spreadsheet to come up with the Hansen solubility parameters.